So I'd like to introduce Wei-Ning Hsu, who's a graduate of MIT and CSAIL over here, who's in Jim Glass's lab. Now he's at Meta Fundamental AI Research, and he's going to be talking about some self-supervised learning work.
Good morning, everyone. Can you all hear me? All right, thank you. Thanks for waking up early and coming to this talk, and thanks for giving a great talk first. Give me a lot of pressure to continue after that, right? So, hi everyone. My name is Wei-Ning Hsu. I'm currently a research scientist at Meta Fundamental AI Research, which the same acronym FAIR again, right? We just changed Facebook to Fundamental. So today I'm going to share our past 2 years effort on self-supervised learning and specifically for speech generation. And outside of this topic, I also work on multi-model self-supervised learning and unsupervised speech recognition and other self-supervised framework like data2back, but I won't be covering those topics for today's talk, but happy to discuss more during coffee break or when we grab a drink in the evening. All right, so let's get started. So this talk would include a lot of joint work with my wonderful collaborators at Meta. So for the sake of time, I will skip naming names. Right, so for the introduction. So self-supervised learning, as I believe most of you are aware, that have achieved great success for the past few years and has huge success, especially on automatic speech recognition. So it is extremely label efficient. So let's maybe take a closer look at the bottom left figure. So we see that on the leftmost bar, it is from a model called Noisy Teacher, which is effectively a semi-supervised learning algorithm. It is trained on 100 hours of the supervised data, then pseudo-label the rest of the data, and then train that again. So on that framework, we achieve 8.6% weighted rate on the test set. And then if we pay attention to the rightmost bar, which is from Wave to Back to, also one of the state-of-the-art self-supervised learning pretraining framework, we see that with only as few as 10 minutes of the label data, we can achieve the same weighted rate, which is 8.6. So it is 60 times less data compared to the Noisy Teacher. And moreover, we also found later on we can use such self-supervised implementation paired with adversarial training to build a totally unsupervised ASR model using just unpaired text and unpaired speech. And it can actually achieve a weighted rate of 5.9, and this is on par with the best supervised model trained with 4,960 hours of the label speech from about 3 years ago, as you can see the spec augmentation from 2019 from Google. So this is definitely impressive. And beyond automatic speech recognition, self-supervised feature also benefit many other speech tasks. So for example, these are the tables I snapped screenshots from the Superb paper, which is an excellent benchmark paper. So it benchmarked various self-supervised implementations on a number of tasks like phone recognition, keyword spotting, intent classification, speaker ID, emotion recognition, etc. So covering speaker-related tasks, content-related tasks, intent, semantic, paralinguistics. So we can compare first the number highlighted in purple, which is the traditional feature filter bank of us have been using, with the self-supervised feature on the bottom, which is from Huber. So we see across all different tasks, self-supervised feature when paired with the same prediction head, same model taking different feature as the input, it achieves much better performance compared to the baseline feature. All right, so now I've talked so much about self-supervised learning. Let me just give a very brief overview on what self-supervised learning is. So in a nutshell, what it tries to learn is a good feature extractor, and we want to use a lot of data and less restricted. So we're going to use unlabeled data to learn such a feature extractor. So to do so, we need to define some pre-text task from unlabeled data. And this task may vary depending on what data we're using and also what downstream task we are more interested in, right? So here are a few more famous and prominent example. So for example, for text pretraining, people have been widely using a BERT, which does mask prediction, where you mask part of the token and you predict that, right? So mask language modeling. And for image MoCo does this instance level contrastive learning, where you perturb an image and you randomly sample another image and perturb, and you use the ground truth image to see which one correspond to the original image, but perturb, and which one is not. So it does this instance level contrastive learning. And combining these two approach, and for speech, wave to vec 2 is a dominant approach which does like frame level contrastive learning. So instead of like taking the entire instance and perturb and do instance level discrimination, it does like frame level discrimination, trying to determine like which one is the mask frame. All right, so once we decide what task to use, as shown in the diagram here, we're just going to train like using unlabeled data with this like pretext task, and to train this entire model, which is composed of like a feature extractor and a pretext task head. And once pre-training is done, what we're going to do is just to remove this pretext head, because like it's not going to be needed anymore. And then we're going to stack whatever like downstream prediction model we want to use. Basically, you can imagine we just like replace filter bank with like this like feature extractor, which is learned from unlabeled data, right? So we can stack, for example, a linear layer paired by CTC loss for like automatic speech recognition, or we can also stack a decoder for like speech translation or speech to speech translation. So take ASR, for example, which is like stack a linear layer followed by CTC, and it produces like posterior probability over characters, and we train the entire model like as if we are training like supervised model, right? Like end to end, or frozen, like depending on how much data you have and what you want. Right? So like so far we see like self-supervised learning are primarily used for discriminative tasks because it produces like good features for speech, right? So we have now a better feature extractor than handcrafted feature. Condition on which we can easily train an inference model that map like this kind of like feature to like the target space X, either it's like text in the same language, text in different language, or emotion label whatsoever. And in contrast, it is not as straightforward to use it for generative task, which does the opposite. For generative task, what we do is to take the target like X as the input and produce like speech like as the output, right? So how can we do that? So our answer again is we want to bridge like the target X and speech with this like self-supervised representation. So let's review this diagram again. So what we do for inference is we extract feature, right? And we train some inference head, and then we produce like the target X. So for generative task, we're just going to flip the direction for the upper half, right? So specifically, instead of like taking self-supervised feature as input, we're going to take X as input and train a generative model. So it can be a Tacotron 2, can be a WaveNet, right? And then to produce like this self-supervised feature. Because we know like it is easy to learn the mapping from this feature to X than to learn the mapping from like the raw like waveform or filter bank to X. Then the opposite direction would also very likely hold, right? So we're just going to do that. And then because like our ultimate output of interest is speech, then like once we produce the self-supervised feature, conditioning on say like text, we still need to find a way to convert these features back to the waveform, right? Then this is our ultimate output. Okay, so the next question to answer in this framework would be, what kind of like features are suitable for this framework? And there are like several properties, like it's not an exhaustive list, but just like several things come on top of my head. So first, we want it to be easier to predict compared to like predicting raw data, right? So that's the whole point of like predicting self-supervised feature instead of like predicting waveform. And second, we also wanted to retain the information we are interested in. So for example, if it's like speech to speech translation or speech to text translation, we want, for example, like the content related to X are still remained, right? But like some other attributes like speaker, if we're doing say a text to speech synthesis or text to speech translation, then speaker is something we don't necessarily want to encode in the self-supervised feature. We can have additional input to condition on, right? Right. So in this talk, we're going to mainly focus on using Hubert unit, which encodes mostly content. But again, like this framework is not like limited to using Hubert. You can just like swap in like any kind of like self-supervised feature you are interested in, as long as they have the property you want them to have. Okay, so let me again give a brief introduction on Hubert. So it is also one of the well-performed self-supervised learning approach. So the way it works is that given an audio stream, it will first extract some frame level features and train a K-means model to produce like frame level pseudo labels. So this will produce like targets similar to BERT, which are discrete labels. And we have like such label for each frame, right? And then we're going to do the same thing as BERT, which is mask prediction. So we're going to use some like lightweight front-end model to extract frame level features. So you can also replace this part with filter bank feature extractor, a fixed like non-learnable one. And once we have the frame level feature, we just like randomly mask some spans, and then we pass it through some transformer model. Then we predict this contextualized feature, and we predict like what the cluster identities are for the frames which we mask at the input. So we construct the same mask language model task, which require the model to do acoustic modeling by understanding the content for the frames which you observe, and also infer what's missing, right? So it does like mask language modeling implicitly to solve this task. Okay, so after this model is trained, right? Initially, we mentioned like we create this target using MFCC. And as I think most of you are aware, like MFCC are not that good. It produces like feature or like clusters that has non-trivial correlation, but not perfect again. But after we train this model, we can use that to extract better features than MFCC. This is the whole point of doing self-supervised training, right? So once we have these features, we can use them to do k-means clustering again to produce like better clusters, right? So we can redo this process over and over again to gradually refine the target and then refine the feature extractor and then refine the target, right? So this goes on and on until it saturates. So this is what we do for the second iteration. Okay, so now let's see if like we can really do that by first confirming we can really invert these like self-supervised features back to the waveform, right? If this does not hold, then like all of the framework does not like work at all. So I'm first going to talk about like the Vocoder part. So by Vocoder, like I'm using that in a like very, generalized definition. So usually Vocoder refers to when you convert say spectrogram features back into waveform. But here we're going to convert these like self-supervised features and in particular like quantized units back into waveform. Okay, so here's our first like preliminary experience where we use a modified TTS model. Instead of like taking the say text as the input, we take these units as the input. So we're just going to modify like the tacotron 2 to do this task. So as I just mentioned, so once we have this spectrogram, we can infer the frame level units with this like Hubert plus k-means, and then we will produce like these frame level units like 17, 17, 17, 32, 32. And then we're going to remove the duration information. So it's going to be like just 17, 32, 49 here. And then we're going to use that as input and feed into tacotron 2. All right. So we are like this Hubert model is trained on Libre speech. And we're going to like train this top model on LJ speech, which is a single speaker data. And now I'm going to play some sample. So now I'm going to first play the original sample.
Within minutes, Tom was in charge of clearing away rubble and extricating anyone who might be trapped inside the buildings.
Okay, and here's the resynthesized audio from Hubert units.
Within minutes, Tom was in charge of clearing away rubble and extricating anyone who might be trapped inside the buildings.
And let's hear now an example from a different speaker. And here's the resynthesized results from Hubert.
What bankrupts in the world we feel in death, let some remorseless predator seizes on all we found without our life. Which wins?
So what we can infer from like these audio samples that like once we encode like the information into Hubert units, it preserves the content, but not the speaker identity, right? So when you infer like just the content and train a single speaker TDS model, it learns to retain the content while like synthesize in the different voice, right? So this definitely confirmed that like this encodes the content information, right? So the next thing we want to do is to improve like this vocoder. So as you can previously hear, like the prosody, like the speaker information is not like encoded, like reconstructed like faithfully compared to the original audio. So next we're going to like propose like a disentangled like speech codec with self-supervised units. So we're going to have like separate streams, one for content based on the self-supervised units, one for speaker using just a pre-trained like speaker encoder, and the other for prosody, which just like extract basic like prosodic feature like F0, speaker normalized F0 to be precise. So this is like we're going to adapt from hi-fi gain, which was originally designed as vocoder that takes spectrogram as input and waveform as the output. So now, as I mentioned, we're going to plug in 3 corresponding streams so we can do disentangled control. One with Hubert units, the other for pitch, quantized pitch, and the other for speaker embedding. And now again, I'm going to share some like resynthesized result. So I'm going to focus like comparing two type of like units for content encoding. One is Huber, as I previously showed, encodes mostly the content, and the other is based on vector quantizing VAE. So this is a reconstruction-based model. So you can imagine the codec would encode not only the speaker information, not only the content information, but everything, because it tries to reconstruct the original speech. So it also encodes the speaker information. So keep that in mind. Okay. So let me first play the original sample.
I've been in 2 finals and I've got a medal.
Okay, so now let's first listen to the resynthesized audio from Hubert.
I've been in 2 finals and I've got a medal.
And another one from VQVAE.
I've been in 2 finals and I've got a medal.
So I believe like from my year, like they behave like similarly in terms of like resynthesis quality. We do have like more quantitative results in the paper showing like comparing the F0, how well it reconstructs the original F0, how well it predicts like it resembles the original speaker, and how well it preserves the content with the help of an ASR model. So now the more interesting part is like, what if we want to like change some of the attribute for the resynthesized speech? So we have like some more experience in the paper, but here I'm going to show if we swap with a different speaker embedding. So now again, like this is from Hubert, synthesizing in a male voice.
I've been in 2 finals and I've got a medal.
Okay, and this one is from VQVA. And remember that like the original audio is from a female speaker, but now we try to condition our male speaker embedding. So now let's hear what happens.
I've been in 2 finals and I've got a medal.
So you can imagine, you can hear that like it's not disentangled because like both the content units and the speaker encodes like speaker information, and they sort of like conflicts in this case, right? So you hear like some abrupt change of the speaker attributes, like in this recording. So this definitely shows like the strength of this having this disentangled codec. And again, like this framework does not use any text supervision. It's totally unsupervised. All right, so now that we have like assured ourselves that like we can use this codec to like represent the content, and it is also discrete, so we can use that to do a lot of like interesting things. So in the first part, I'm going to focus on unconditional speech generative modeling, where you can imagine we can do something similar to text, which is train a language model, but on these like units, and then we can produce like natural speech. So the background, oh, I just mentioned some of those. So I think like many of you have seen like we have witnessed like a lot of like amazing results from like training large language model, right? Like doing like web crawl and like show that this language model, once just like trained with web text, it is capable of doing this like zero shot text understanding, or doing like grammar correction, or like text continuation, or even write a paper for you maybe. Yeah, so this is definitely amazing, but we haven't seen such capabilities like for speech. And speech is more complicated because it has to not only model the textual content, but also has to make sure like the prosody is coherent, and like the way like there could be not just like one speaker. It can be also in a conversation where there are more interactions between like multiple streams of the content, right? So it's definitely more challenging and more complicated. So we want to start like exploring, can we do that for speech? Okay, so our first attempt is a model called Generative Spoken Language Model, short for GSLM. So this is the first text-free unconditional language model for speech, which is capable of synthesizing like more or less reasonable content with some learned vocabulary. So what we do is very simple. We just like replace like character or BP in text with self-supervised units, and we don't do any BP. So we just encode this like deduplicated units, as I showed previously, 17, 32, 49, right? And for this particular model, we train on LibriVox, a subset of that, which has about like 6,000 hours of audiobooks. And then we just train this model, and we just want to see what it can do. So I'm going to, again, like play some audio samples here. Right. So what we do here is something interesting. We just like give it a prompt, right? And once we finish the prompt, we let the model to continue do generation by doing like temperature-based sampling. So this is the prompt.
He took no notice of her.
Okay, so keep in mind, like this is just a prompt. And then we have like what we generate by continuing this prompt. So the first part will be identical, and after that, it's going to be generated.
By one of the women, he took no notice of it. He looked up and saw that it was a great pity. He saw the baby who was being cold.
Right. So I don't fully understand what like that person is talking about, but it definitely has some grammar and probably refer to like the right like pronouns, for example. And we can also hear to another example here.
This reality begins to explain dark power.
And this is again like continual generation.
This reality begins to explain the dark power of determining perception and believing that the pressure of emotion which contains that power.
Okay, again, like it's saying some words which I don't fully understand, like the motivation or like the topic discussing here. But yeah, it's interesting. And as a baseline, we can also hear to like if we just naively quantize, say like male filter bank, and this is what we are producing.
And by the woman, he took no notice of her.
So this is like cried one of the women, he took no notice of her, right? But like these units are not good. So this is like what it can do with resynthesis. And the continuation is just like murmur.
There, verse 6. Hi, that's the drugs.
So no, this is probably just like baby mimicking the sound produced by their parents without like uttering any like meaningful words here. Okay, yeah, so these are conditional samples. And we can also just like let the model go well and not like providing any prompt, just like start of the sentence and generate the entire sentence. So this is one unconditional sample from Hubert.
Now we shall be there, they said, and I will go into the line to pay the price for them. They went on as well as many other best people. They went into the big back room where we were, they said.
Okay, some storytelling, it appears. And I think like one of the interesting I want to highlight is like we can also do similar things with like first transcribing the speech with like ASR system, right? And then like pair the ASR system with the language model and then resynthesize. But then like you can hear this is an example. So I want to highlight that there was a pause in cried one of the women. He took no notice of her. But once you transcribe that into text, you don't preserve all the information like pause or like back channel or laughter in text, right? So you lose such information when you resynthesize that. So this is definitely one of the caveats of like doing things in the text space instead of like a learned unit space, like better characterizing speech. Okay, so come back. This is very exciting for our initial attempt, and we didn't do much of the tuning. We're just like stuck in like the language model in Fair-Seek and train the model and worked. And so the next thing we want to emphasize more is like, how can we better, like recover or like continuing in a coherent like prosody, right? So as I showed previously, like the unit does not encode much about the prosody, but if we train a vocoder and feed in like this prosodic feature in the vocoder, then it can also synthesize like the original like prosody. So what we do as our follow-up work is called like ProsodyAware generative spoken language model, which is an extension of a transformer language model that instead of like only having one stream for each time step, we now have like 3 streams here. So each, in addition to the original unit stream, we have one more stream for like the prosody unit and another stream for duration of that unit, right? So condition on this, we can reconstruct the inputs for like the neural vocoder we just mentioned, adapted from HiFi and synthesize more expressive speech. So again, I'm just going to show some like demos here. Okay, so this is the one. So now let's again listen to a prompt.
Love is a babe. Then
so you can hear like the voice is like slower and like lazier, right? So now let's maybe like listen to a baseline example where if we just like predict the units without like the prosody, then what the we still like feed in like the units, but and predict the prosody, but now like the prosody is not at the input, right? So when we're predicting the future prosody and the future content, it does not see any information about the prior prosody, but it does see the information about the prior contents. So this is what it sounds.
Love is a babe. Then we shall possibly be put to death, because it is Abram's place, which possibly would not permit grace to come to and bring people to the Lord.
So what you can hear is that like it originally like speaks in a slower like pace and like a lower tone, but after the continuation, it reverts to the, I would say like the average pace and average tone, because it does not see like what in which kind of like way the sentence was being expressed. And this is our proposed model, which takes in like prosody input and also predicts prosody.
Love is a babe. Then he thinks that many tears should fly into my brain and be still that vulture of doves in all their conflict,
Okay, again, I don't know the meaning, but like the prosody sounds like more right to me because it's a similar pace. Yeah. So yeah, so this is again like what we show with like if we have the prosody at the input, it would like first like prosody is definitely correlated within the sentence, right? So if you switch the prosody of the first half and the second half, it doesn't definitely sound like incoherent. And second, we also show in some of the quantitative metric that we can see whether we compare whether we provide like prosody at the input or not, and we measure the prediction error in the teacher forcing mode for each of the 3 streams. So first of all, we will expect that like prosody is correlated. So if we don't condition our prosody input, then the prosody prediction would be bad. But second, more interestingly, we also found like the negative log likelihood for predicting the content would also improve if we provide prosody. So at a high level, it means like prosody does not just like change the prosody of the future like sentence, but it can also change the meaning or of the words or the words we choose to not continue like the rest of the sentence, because it definitely carries the meaning and the semantics. So this is like the takeaway from like these studies. Okay, so moving on, as I mentioned, like speech is more than text because like there will be scenarios where we have like multiple streams of the speech, right? As in conversational scenario or like in podcast in interview. So our next effort along this line is called like dialogue GSLM, which aims to generate a dialogue. So again, we extend from the previous framework by now creating a pair of like language model here. So you can imagine like each model have the identical parameters, but just like take different streams of the speech as the input. So you can imagine each language model is modeling like one speaker. It has the self-attention to attend to its history, but it also has the cross-attention to attend to what the other people have said like in the past, right? So it's kind of like the 2-string Siamese network for language model, and condition on which we can generate like realistic conversation, or to some extent. I'm not so sure about the content. Okay, again, let me play the sample, which is very exciting. So this is the, let me see, the prompt.
Name is B. How are you? What's your name?
Right, so this is, maybe I should mention that. So this is trained on the Fisher dataset. So Fisher dataset is like phone conversation. So people are paired randomly together and they were like assigned a topic and they have this phone conversation trying to, like first like greet and then like talk about like some assigned topic. So you see like it always start with like, hi, my name is, what's your name? And something you want to also notice is like, you can see there are 2 streams of the waveform here. And in real conversation, there are definitely like overlapping of the speech, right? Because like when you do back channeling, like you won't like necessarily wait until someone like finish their sentence, right? And it's also important like when like this back channeling is like done. And also there will be some other example. Let me play this one with like laughter.
Yeah, growing up, I listened to Andrew Baker play a lot. Now that's some, yeah, that's some off-color humor, but I think.
Yeah, so you can hear like there's laughter, and in typical like text transcription, you also don't have that either, right? So this is another reason why we directly want to model speech instead. So let me play the sample. So this is like our continuation for the first conversation prompt I just played.
Hi, my name is B. How are you? What's your name? Debbie. Where do you call it?
Wait, I think for some reason it to 1 stream. They're supposed to be 2 stream, but okay. So unfortunately, I think like the audio here is really encoded like in stereo, but like the speaker here only plays 1 stream, so that's why it sounds a bit weird. But actually, it's all right. I think like so all these like samples like demos are publicly available. So I would really encourage you to just like go to the website and listen to those samples and just like trust me. So what I want to show here is like just like trust me. So. Or we can look at the waveform and do like waveform reading, not spectrogram reading, unfortunately. But okay, we can see like for the continuation part, we see like there are definitely some like waveform, like non-silence part, like emitted when the other people are speaking. So some of those correspond to laughter. And some interesting thing you can observe from the second example is like once like one party start like laughing, the other feel like obligated to also like laughing, even if like the content, which from what I heard, like it's not so interesting, but like they still respond to each other politely. So yeah, this is like what I want to show from this sample. Yeah. So definitely like, again, this is like why we want to model speech directly. Okay, let me go back to my slide. Okay, so right? So that concludes the first part, which is about unconditional spoken language modeling, which we show first like just the content, and then we extend to model the prosody, and later on we extend to model like serial like conversation from like multiple parties. So in the second part, let's maybe like talk more about more concrete and like useful applications here, which is like conditional speech generative modeling. Okay, so the first application I'm going to talk about is direct speech-to-speech translation. So there are many ways one can build a speech-to-speech translation model, as shown on the diagram on the bottom, right? So we see like the most modular way would be we can first deploy an ASR system in the source language, and then deploy a machine translation model to convert from source text to target text, and then build like a TTS model on top of that, followed by a vocoder to convert maybe like a spectrogram back to waveform, right? So this is the most modular approach, right? And then later on, like I think over the past few years, people have found like combining the bottom two, like MT and ASR, actually give you better performance, because like you can imagine if you train separately, the benefit is like you can use more data, right? You can use separate data for each part. But the downside would be there would be like error propagation, and the entire system is like not optimized toward the ultimate goal. So people have found like jointly training speech to text translation model would outperform the cascaded system. And like later on, like with the help of like pre-training each individual module, for example, the speech translation model, you can have say wave to back encoder for like the speech encoding part, and like Embark decoder for the decoder part, right? With the help of this like pre-trained module, you can use more data, and like there will be less issue of like the difficulty on collecting like parallel speech to text translation data. So yeah, so we have like shown previously like these two have worked, and then like moving on, we also want to show like we can directly build a system for speech to speech translation without emitting intermediate output. So one of the strong arguments we have here about why we want to do that is first, less error propagation, second, faster. Third, also like we can support unwritten language for the target side, right? So for the second paradigm, we still rely on like target side transcription to produce like the intermediate output, condition on which we synthesize back into speech. But like there are also many languages in the world, or like dialects where like it's not written by most of the people who use that language. For example, I speak Taiwanese, although like there are like annotations or like linguists coming up with some like system for annotating Taiwanese, but like this is not like every Chinese speaker can do. And similarly, maybe like for Swiss German or like many like Chinese or Arabic dialects, right? So it is definitely of great importance to increase like the coverage to like more unwritten language. And another strong argument we can make here is that, again, like once you convert things into text domain, you don't preserve the prosodic information from the source speech, right? So the same sentence, when spoken in different prosody or in different contexts, they can mean very different things, right? So this like you need to like train the entire model like end to end in order to preserve like such information. All right, so so here's like the system we developed for direct speech to speech translation. So we follow like this translatotron pipeline, which is composed of this like speech encoder, which is shared. And then we have like 3 separate decoder. One decodes directly into target speech spectrogram. The second one decodes into like target text. And the third one decodes into the source text. So this part you can think of as an ASR speech translation and speech to speech translation. So this is like the base model we adapt from. And during inference, we can remove all the text decoder and just like use the speech decoder. So this is Translatotron 2, not our work. And for our work, what we propose here is to replace the target spectrogram decoder with the target unit decoder, because we show it already encodes like most of the content information there, right? And then we also propose to add an auxiliary CTC decoding objective, taking the decoder intermediate layer representation as the input and decode into the target text. So now we're going to be mainly comparing like these two systems. So with the same 2 auxiliary tasks, and we have 1 additional auxiliary task, we show that like on the Fisher English to Spanish translation datasets, the Translatotron 2 achieves an blue score of 25.6 here, and the cascaded system we built achieved like 43.9. And if it's like 2-stage cascaded, which is like S2T followed by TTS, it is 42.9. And our system on the left is like 39.9. So it is not that far away from the cascaded system, and also significantly outperform like the translator tone baseline we compare with. And later on, like the paradigm we just mentioned, it still require like the target text and also the source text. So let's assume like we don't have like target text. So as in like target text, target language might be an unwritten language, right? So we cannot use our CTC auxiliary decoder anymore, and we don't have this like target text decoder anymore. So in this condition, we showed that like what translator tone like performance drops significantly from 25.6 down to 7.2. Our performance only dropped from like 39.9 down to 35.2. So it's still a usable system. So we support unwritten language. So next, what if like the source is also unwritten? Then we cannot use this like ASR auxiliary task. So what we do here is to remove like this source text decoder. But again, we can still do a source unit decoder, which transcribe into this like pseudo text represented with self-supervised units, right? So in this case, again, like translator tone has a blue score of like 0.9, basically not producing anything, probably just like silence. And our model still have like 31.8 performance here, down from like 35.2. So again, it's still a usable system. And the closest baseline we can find is called like UW speech. So I believe it learns some like codec using ASR data, not from the target language, and then use that codec to do similar things as we do here to train the speech to unit translation model. But maybe because like the codec they learned was not as good as like Hilbert units, so the performance was only like 9.4 here. Okay, so moving on, how we can further improve this like speech to speech translation pipeline. So as I mentioned, for speech to text translation, people have found like many useful tricks. For example, pre-training the encoder with wave to back, or pre-training the decoder with Embark, right? But like Embark decoder is only used for producing text because it is trained for unpaired multilingual text denoising autoencoding with a sequence to sequence model. So as you can see, like units here are actually very similar to text, right? So whatever we do with text, we can just like do the same trick with units. So what we do here is to do this like Embark pre-training, which is a sequence to sequence denoising autoencoding, and replace text with unit. So now we can take unpaired speech and do this like decoder pre-training, right? And now like following the same framework, which like for S2T, it is like plugging in a text and bar. Here we're plugging in like a unit and bar. And we also show it improves the performance. So let's maybe like look at more specific numbers here. So we show that like we compare on two directions, English to Spanish and Spanish to English on like, I think 5 or like actually 3 different data sets, Europower, must-see, Covost, and MTEDx. So we see that like on English to Spanish direction, maybe it's because like the encoder is more, maybe because like it's an easier task. So we see that like the S2U without multitask learning still managed to get reasonable performance like 23 and 25 here. And for S2U with multitask, which is what we showed earlier with the auxiliary decoder, it improved the performance to like 25 and 26. And moving on, the following two are just like reusing the pre-training thing. So if we pre-train the encoder with wave to back to large, then the performance like jump from 25, actually like from 23 to 30.8, because we don't do any auxiliary task here. And we can further improve that by also pre-training the decoder with the unit and bar I just mentioned. So the performance would be further improved to 32.2 here. And you can see similar trend on all the other evaluation sets as well. So the takeaway here is like, you can, whatever you find useful for text, just like try it for units, and it most likely would also work. Yeah. All right, so the last application I'm going to talk about here is this like text-free emotion conversion. So again, like we want to synthesize like or convert the speech like while preserving the content. So we want to synthesize the same content but in different emotion. And previously, like people have like done a lot of work on that, but mostly they are doing like a frame level mapping, just trying to map spectrogram and convert like maybe the value for each spectrogram. But as you can imagine, when you say something in different emotion, it's not just like you change the sound texture for each time frequency bin. You may also change like the tempo, like the pace, right? And also maybe like for happy, you would insert some laughter in it, right? So it probably requires more than like per frame mapping. It probably requires something like a sig-to-sig model, right? And so what we do here is to formulate this problem as a machine translation problem, where we have like, we are trained on parallel data where we have like source and target speaking the same content, but in different emotion. So what we do is we just transcribe them into units, and note that like the unit here are not necessarily the same between the source and the target, because like, first of all, it's not like the perfect transcription of the phonetic units. So the same form might be still represented with like different units here. And also because like the target and speech might have like different lengths. So some of the like speech might have like laughter in that. So there might be some segments in one side which inferred additional additional information like laughter here. It's the same speaker, yeah. But actually, I think we also have a speaker embedding here. So this is something we can also convert, because like we are using this high gain vocoder, right? So they are disentangled, right? And the emotion here we model is more about just like what units it uses and what like pitch information it uses. Okay, so let me go back to the sample, and this is mono, so we don't have to worry about like the sound system. Okay, so this is the source speech.
They were deep in the primeval forest.
And this is the generated one. I believe it wants to sound like happy.
They were deep in the primeval
Yeah,
forest.
by inserting some laughter, it definitely sounds like happier than the first one. And I think like the second one is like neutral to sleepy.
You mean for this state, General Alberta?
And I think this has some yawning.
You mean for the state, General Alberta?
Yeah. So yeah, so as you can see, this is a very powerful paradigm. You can also use that for emotion conversion. It does not have to be frame-wise matched. You can just formulate that as a sequence-to-sequence machine translation task here. Okay, so final remarks. So why do we want to use discrete self-supervised representation instead of text? So as I iterate like over and over again, like text is not an ideal transcription for speech because it missing a lot of like information which we care about like in speech, especially in more expressive like speech communication. And text-based method also leave out like the unwritten language, right? And we also want to make it more inclusive. So we want to develop things which we can still use text, but does not require text for all the languages. And why we want to use self-supervised representation instead of spectrogram. So we showed that like it is more compact and more disentangled in a way that like whatever target you want to map to or map from, it would be easier, like given the same like model capacity, right? And like we can try to reuse the same like representation over and over again, and we don't have to retrain like one self-supervised model for each task. So the universality of self-supervised representation is definitely a key feature we want to like advertise here. And again, it also makes it easy to use like text-based method because we can quantize that without losing too much information. Okay, so what's next? So we want to like, now we have seen that we have enabled many speech application. We want to just see like if there are more we can like explore, right? With this like new technology, maybe we can now imagine like more applications like derived from like such innovations. And we also want to have like better vocoder and self-supervised units because like go hand in hand. Like once we improve one thing, we can improve like every system we develop like based on self-supervised units. And we also want to do like multi-model generative models. As you can imagine, like it's not just like the audio which have correlation within like this sample. Like how I talk like would also correlate with like my, for example, my face appearance, right? And also like maybe more widely like the slide I'm using here if you are watching the entire video, right? So we also want to do multi-model like inference, self-supervised learning, and generative models here. And we also want to do like more disentangle like codec for audio beyond speech. So you can imagine now maybe like we want to not only preserve what's in speech, but also what's beyond speech, like room acoustic and also background noise. Can we also separate that and encode that? Or do we have a knob where we can decide when we want to preserve that or when we want to remove that, right? So it will enable like better controllability, all right? So this is the reference for, I think, most of the paper I cover in this talk. So thank you. Happy to take questions.
Questions? Well, thank you for the fantastic talk. I was wondering if you could maybe comment on the complexity of computing the employees.
Yeah.
My intuition tells me that the more that it's kind of a non-supervised or self-supervised, the more it is carry out the same kind of something. So I was just wondering, what might be the throughput of the codec that you're pushing?
Yep. Okay. Yeah. So let me rephrase the question to make sure I get it right. So you're saying like, can I comment on like the complexity of the codec, right? So specifically, do you mean like how much time it takes to infer this code and like how fast it is to convert this like code back to speech?
Yeah, I mean, I guess I'm just interested in like how long it takes to actually compute the keywords units.
Like during training or during inference?
During inference.
Okay, yeah. That's a good question. So I don't have like concrete number on top of my head, but what I can comment on is like the units we infer. The Hilbert model is a 12-layer base transformer. Each layer has like 768 dimension for the embedding, and like 4 times like the size for the feed forward. So whatever complexity you see like from computing BERT embedding, it's pretty much the same as Hilbert. Yeah. And for the codec, like the hi-fi gain, it's just like as fast as hi-fi gain because we only modify the input and output, and the architecture is the same. Yeah.
Hi, this is the I have a quick question on the generative part and the third part that was demonstrated. I see here that although it's speaking like natural speech, it's speaking words that are grammatically correct, it's not speaking words that make sense, which is not the case on your scene large language model. What do you see could address that? What are you planning to do to address that? Like, do you just have more training data like we use in large language models, or you somehow integrate the large language models or some other thing?
Yeah. So the question here is like for the unconditional generative model I showed at maybe like the first part of the application. It is generating like human-like sound, but like the meaning is not like, it is not very meaningful, right? So how can we improve like the quality of the generated content? So I think like, first of all, I would just say like the easiest solution and the solution everyone goes to is just to get more data, right? So if you compare like the amount of data we use here versus like how much data like this large language model uses in order to get those impressive results, you'll find like it's just like a tiny fraction of those. So here we're using 6,000 hours of the speech, right? So 6,000 hours of speech, you know, like from Libre speech, it's like about like 1,000, right? And 1,000 is about like what, like 23 million or 2.3 million sentences, right? So 6 might be like, I don't know, like 13 or something million sentences, right? And like for text, you can see it is trained on like billion or trillions of tokens. So the scale of that is like definitely different. But another thing we can find is like, I also believe it's not the only way to improve the efficiency here. So as you mentioned, like how we can combine like text like with speech for training a joint like language model is definitely some topic we're very interested in, right? Because like we don't want to just like train exclusively on speech. We can leverage whatever resource we have to learn better like in both domains, right? And the other thing is like, I think what codec we use also make a big difference, because previously we have also tried, you know, like as I show, like quantizing log melter field banks and train a language model, or even use like VQVAE code to train a language model, but those models doesn't work. And I believe the main reason of that is because like that codec is not very disentangled. So you put more burdens on the language model by having to model not just like the content, but also know like the speaker or like the background noise like information, right? So I think like a better codec would also improve like the efficiency here. Yeah, so the question is about the vocoder. So the vocoder, as you can see from this slide, we take the deduplicated units, which means like we remove the duration here from the input. And the question is like how we recover like those units. So I think it depends on the model. So the first model we trained here, is Tacotron 2, right? So you know, like Tacotron 2, the input is text, right? And it's like text as is without like predicting the duration for each character or each phoneme, right? So the way like this model is able to handle is just to train a seq-to-seq model, learning to model like the duration for each input like token, right? So for this model, it is like the same as like treating units as text, right? And the model figure it out. So for the other model, the hive again here. So when we train this model, we don't deduplicate the unit. We use like the frame level units. So the question now comes to, once we predict the deduplicated unit, how do we like append its duration, right? Repeat like the number of times. So we just like use a very simple duration predictor inspired by fast speech 2. So you can basically add like a convolutional network to predict the duration for each of the module, for each of the token. And that's how we recover the duration.
I have one last question. Gary.
Thank you very much. And you mentioned about that, we can generate one that is so managed without to transfer, not only for context, is that if we like to build such a model, actually we need the parts piece there, right? So you mentioned that unwritten piece there. So that someone needs to speak the same things in the different languages. And also you mentioned that we have a parliament there in European language, and we have tons of it, but every language has a different way to transfer that linguistic information. If we translate the English piece to Japanese, actually the piece is totally to translate. So instead, you just directly transfer that it's the different language that is very difficult. And you mentioned about that dialogue. And the dialogue is, if I speak to one person and another person, actually the piece is also different. Even the content is the same. This is because the relations between the two is different. So how do you solve this problem?
All right, so let me rephrase this like very, very great and like very important, but like also very long questions. So the question is about, okay, for speech to speech translation or even like modeling dialogue, right? So it really takes like real pair data for us to train such model. And like the specific example she mentioned is that, for example, even if like we are having the same conversation, but like when we are talking to different people, then like the pitch or like the way the wording we use like would be different depending on the relationship, right? So how can we approach that? So I think like this is a question I would like to discuss with everyone, because we don't really have the right answer to that. Of course, like the simplest approach would be collecting such data, right? That's the whole point of like first building this like end-to-end training pipeline. So once we have this data, we can explore this framework to model the relationship, right? But again, like collecting such data, especially let's take speech-to-speech translation, for example, would be very difficult because, as you mentioned, like if we want to preserve the prosody information, we need to make sure like the input and output not only preserve the content, but also speak in the same prosody, right? So, and it's probably would be better if it's from the same speaker, right? Because like the same speaker, like different speakers tend to preserve prosody in a different manner, right? And it will be easier for us to train like that model because we remove another like variation there. And but like to do that, we need to find like fluent bilingual speaker and then record tons of like, like parallel data, which include like rich information and like which preserve in both source and target. And the specific one data set Charlie mentioned is that the Europower data, I think Vox Populi data set recorded from like European Parliament. So it is like parallel speech data where like someone is like giving a presentation on the stage and there will be like simultaneous interpreter like to translate that into different language. But I also want to emphasize like this is not the perfect data set for doing this because first, like they are interpreter. They try to summarize things, or so it's usually shorter and it's not like try to preserve like the process information, or like process information is probably not there. Even if like, like someone's giving an angry speech, the interpreter won't just like yell at their ambassador, like in the same tone, right? So it's probably not the best, scenario for preserving such thing. So what I do believe is like, we do need to leverage more on pair data to learn the general, like correlation between like prosody and the semantic given the context, right? And then we can more efficiently use like small amount of like pair data, which we still need to like build this relationship for the translation model. Yeah.
All right, I think we're out of time. Let's thank Wei-Ning for his business.
Thank you, Ron.